Here are a couple of application questions using exponential functions. So hopefully you've all seen Back to the Future, but Marty McFly and Doc need plutonium to create the 1.21 gigawatts necessary to power the DeLorean. The half-life of plutonium is 24,000 years. The original pellet that they used, I have no idea how heavy it was supposed to be, so I made up a value of 0.5 kilograms. Let's find the amount left. If the function is written for the amount left after t years, let's find the amount left after 25 years into the future where Doc and Marty had planned to go. So again, they've already written this function for us, which is very nice of them. And essentially they're saying let t equal 25. So I'm going to find a of 25, which is 0.5 times 1/2 to the 25 over 24,000. So I'm assuming that we're going to have quite a bit of plutonium left because 25 years, not a ton when the half-life is 24,000 years. So if you're not very sciencey, the half-life essentially is the amount of time it takes for half of the mass to deteriorate. As we can see by our calculations, that we should have almost exactly what we started with 25 years in the future. So 0.4996 kilograms approximated to the nearest 10,000th would be how much of the plutonium was left 25 years in the future. So not much of it has degraded to this point. Here's another example for us to do together. So the population of Winnemucca, Nevada can be modeled by that function, where t is the number of years since 1990. So looking at the function, let's talk first about what's the population in 1990 and what's the percent growth. We should be able to find both of those by looking at this function. So here, this is always going to be our initial value. So the first question says, what was the population in 1990? The population was 6,191 people. What is the percent growth? Well, we know in here, that's generally where we're taking 1 plus or minus the rate. And so the rate in this case obviously is 4% because we've added it to the 1. So it's a 4% growth. Now I'm asking, according to the model, what's the population in 2015, which means t is the number of years since 1990. So of course we would take 2015 minus 1990 and get 25, and that would be the number that I put in for t. So I'm going to find 6,191 times 1.04 to the 25th. Use your calculator. So according to this model, at the 4% growth rate, it looks like that tiny little town is going to be quite large if it continues to follow this growth model. Hopefully they can handle it. Here's one for you to try on your own. So press pause, try both questions, then press play to check your work. As you can see, again, they were very nice to us and they've given us the function. And we know that this is a sample that's degrading because in the inside of the function, the one that is being taken to the power, that value is less than 1, which means is essentially when they started it was 1 minus 0.5. Okay, so that's where we're getting that value. We know it's going to be decreasing because this value is between 0 and 1. If it was greater than 1, it would be increasing. So how much cesium-137 is present after 20 years? Well, they tell us that t is the number of years. So I'm going to find a of 20, which means 2 and then 1/2 and then 20 over 30. Again, we're just going to use our calculators to find that result. Start with 20 over 30, take 1/2 to that power, then take it times 2. And it looks like after 20 years, my 2-gram sample has now had a little bit of radioactive decay and is now down to 1.2599 grams. That's, of course, rounded to the nearest 10,000th. After 100 years, of course, we're expecting it to be even lower. The half-life is 30 years, so there should be less than a gram because I'm passing over that 30-year mark. And we can see that after 100 years, we have very little of our 2-gram sample left, so less than 1/5 of a gram left of the 2 grams that we originally started with.